Okay, the purpose of this video is to help you understand the limit definition of the derivative and how you can use it appropriately to maybe save yourself some time when you're solving problems and really just what it means. So we're going to start with a little bit of review of what the limit definition of the derivative is and where it comes from. So I've got a picture on the screen that should look familiar to you, and I just want to remind you that when we're looking at the inside of let's focus on the inside of that limit statement, that fraction there that we call the difference quotient. That is representing the slope of this secant line, the slope between the 2 points x f of x and x plus h f of x plus h. The numerator is really literally y2 minus y1 if we're looking at subtracting the y coordinates. So here's my y2, there's my y1. And then the denominator is x2 minus x1. That's a little bit harder to see, but if I take my x plus h and then subtract my x1, that's giving me the x's cancel out, and that's how I'm getting just the h. So that literally is my slope formula, slope between 2 points. And then as I take the limit, as h approaches 0, the power of calculus is it allows me to say, okay, let's consider as this point right here moves closer and closer and closer to this point, because h, which is the distance between my x and my x plus h is this distance right here, as that goes towards 0, my points are converging upon the same point. And that allows me to give the exact slope at the single point. That would be as if I'm zooming in on that function, closer and closer and closer and closer, and my function becomes almost the same as my line. It looks linear. And there we have the slope at a point, the slope of the tangent line, which we call the derivative. So altogether, that gives me the derivative function. So what we need to interpret that as, because what's happened is we've now learned some shortcuts for finding the derivative. This entire thing here, this limit statement, is asking without any words to find the derivative function. That is, what is the f prime of x? What is the function that I could plug in any point and find the slope at that point? So as we go to the next question, I'm going to be looking at specific examples, I'm really going to be focusing on this limit statement and trying to figure out, okay, what is my function that I'm trying to find the derivative of? Okay, let's take a look at an example of how we might be expected to use this. So we could arguably think that we're in chapter 2 and we're asked to find an actual limit. And we probably could do this by using limit methods if I'm looking at something like part A. But it can become rather complicated to find the limit, and that's going to involve processes of factoring, multiplying by the conjugate, all sorts of things that we looked at in chapter 2. So if we look at what this is really saying, I'm going to propose that this is the difference quotient between 2 points. And this entire thing is really just representing f prime of x. So this question is asking me to find f prime of x, since that entire thing represents the derivative, the slope at the point, the limit of the difference quotient as h goes to 0. So what I need to pull from this question, and a lot of times I will rewrite it, so I'm going to actually take that and rewrite it. Rewrite my, general derivative function. Limit as h approaches 0 of f of x plus h minus f of x all over h. And if I'm looking at that, then I'm really just trying to figure out in what I've got in the red box, how does that mesh with what I have? Obviously, they both have h's on the bottom. And then I'm looking and I'm finding this f of x is what I really want to focus on. And I'm seeing that whatever I'm subtracting here has to be my f of x. So the question is asking me to find f prime of x, right? Remember, that's what this whole thing represents, is f prime of x. Well, if I know f of x, then I can use other methods, my shortcut methods, for finding the derivative. So how I'm actually going to solve this problem involves nothing of doing a derivative. It involves recognizing my function is x cubed minus 1, and then finding the derivative by using my power rule, 3x squared, and that's it. That is my answer. I'm done. So I think you'll agree that once you understand how to kind of work backwards from given a limit that is representing definition of the derivative, how you can use your other methods for finding derivatives, and it becomes much easier. I would encourage you to go back to some of the problems you did at the end of chapter 2 or the very beginning of chapter 3, where I said for a certain function find the derivative, and we didn't have any shortcuts, and you had to set up the limit statement because you got really good at setting that up. But now that we haven't been setting it up, it's harder to work backwards, I think. Okay, so let's take a look at B. So I'm taking a look at this one. Again, I'm looking at this part right here, the inside of my limit, and I'm trying to match that to what I have up here. And it appears that my f of x is going to be this part, that last part of my numerator. So I'm recognizing that f of x, whoops, let's make that legible, f of x is the cube root of x minus 5. And I need to find the derivative. Well, before I find the derivative, I am going to rewrite that one because I want to set that up as a power rule. So cube root can be rewritten as 1/3 power. So if I have x minus 5 to the 1/3 power, now I can take the derivative of that by doing power rule. 1/3 times x minus 5 to the 1/3 minus 1, I'm getting a negative 2/3 power. And that could be good. That could be my answer. We don't generally like negative exponents, negative rational exponents. So it'd be more ideal if I rewrote it. So just to practice how we could rewrite that, let's rewrite that as, again, not doing anything here except just using my exponent rules. F prime would be 1 over the 3's in the denominator, and then the x minus 5 is going to come down as a positive 2/3 power. And we could probably go one step further, right? Because we all know that a rational power is really a radical function. So f prime then becomes 1 over 3 times the cube root of x minus 5 quantity squared. You can put the squared outside the radical. You can put the square inside with the x minus 5 in parentheses. And that would be my answer. Now that one took a little more work. I still think you would agree that that was easier than multiplying by the conjugate, which is what we would have had to do for that radical function if we were going to evaluate the limit the long way. Okay, so now I've got 2 more questions for you to try, so I would encourage you to pause the video and go ahead and try them. See what you can come up with. Okay, so hopefully you had a chance to try those, and I've got my answers up on the screen for you to check out. And I should have mentioned one thing. So I usually look for this right here as my f of x, but you also should be able to make sense of this as my f of x plus h and actually draw your function out from there. So I'm really just looking at this part and saying, oh, that's just my input of my function. Let's just call that x. The input happens to be x plus h, because that's what I'm told to do. But that's really my 2 times x minus 3, same thing as I'm getting here. Okay, so either way, function was 2x minus 3, take the derivative, and it's just 2. So that is my answer. Remember, that is a derivative function in this case, because this whole thing represents your f prime of x, is what it's asking you to find. In this case, it happens to be a number. That means that at any x value, the derivative would be the same, because if you look at your function, it was actually a linear function. So in the past, the other ones, we got something that had an x in it, and that's because I didn't start with a linear function. Part B then, so I grabbed out my function was 2 radical x, and I rewrote that as 2 times x to the 1/2, changing the radical to a 1/2 power, and then did the derivative using my power rule. So I still had this 2 out front, times derivative of x to the 1/2 is 1/2 x to the 1/2 minus 1 gives me a negative 1/2. 2's cancel, give me x to the negative 1/2, which is 1 over x to the positive 1/2, which is also equal to, which is also equal to 1 over radical x. So that is f prime of x that I found, and that is what this limit represents. So I found the derivative. So there's one more step that we should be able to take this to. Okay, hopefully you're feeling a little bit more comfortable with those, and I would say that's a really important skill, but that's not actually the end of where we need to get. So the other connection we need to make is we need to be able to recognize that sometimes I'm asked to find the derivative at a specific point rather than finding the derivative function. So if you recall in section 3.1, we talked about this instantaneous rate of change. Actually, I think this was in chapter 2 that we started talking about it. And we talked about this instantaneous rate of change slope of the tangent line at a specific point, not just the general derivative function. And at that point, I was looking at a specific, instead of x f of x, I was looking at a particular point, a f of a. That just means there's some value, and I'm finding the slope at that point. So exact same thing. Again, we've got this inside of this, I should have used a different color for that. Let's try a different color, and let's go with yellow here. The inside of my limit function, that difference quotient is representing the slope of this secant line between the 2 points. And it's not until I take the limit of it, and then I'm looking at this entire thing, that now I'm talking about the derivative at the specific point, which is going to give me f prime of a. So the only difference here is that instead of doing f prime of x, I'm talking about f prime of a. And then we had an alternative definition of that, which you see down here. And the alternative definition really just involved, it was still finding f prime of a, it involved a different way of labeling my points. Instead of talking about adding a certain amount and calling that h or delta x or whatever you want to call it, we just talked about a different point, a f of a and then x f of x, and talked about if x approaches a, that means this point is going down here and I'm still ending up with the slope of this tangent line. So what I need to recognize is if there's no x in the problem in this kind of scenario, I'm finding the slope at a point. And if it doesn't have an h at all, and it has x approaching a value, then I'm probably looking at the alternative definition. I know an example will help you, so let's try 2 examples. So the first one is, I don't see any h. I'm looking at this x minus pi over 2, or x approaching pi over 2, and x minus pi over 2, and you just kind of got to get used to seeing this and recognizing that this is my limit definition of the derivative. So in general form, exactly what I just had on the other page, limit as x approaches a of f of x minus f of a over x minus a is representing f prime of a. So the question is actually asking me for derivative at a point. So I'm actually going to get a numerical value for this, not a function. There should not be any x in my answer. So what I need to do is I need to start by recognizing what my function is, because I can't find the derivative at a point until I have a derivative function. So I'm going to start by finding my f of x. So in this case, I'm looking at the beginning of it, my numerator and my difference quotient, instead of looking at the end of it. And my f of x is sine x. So what the question is really asking me for is to find the derivative of sine x at some value. Well, what's the value? There's a couple places you might look for that. You might look for that as, because I'm looking for this a, you might look for it right here. You might look for it down here. You might look for it there. All of those are your a value. I find it easiest to look in the denominator because sometimes this guy up here, sometimes this is actually evaluated. In other words, if I didn't have sine of pi over 2, I could have written that as 1, because sine of pi over 2 is 1. And if all you had up there was just a 1 right there, you wouldn't have been able to tell that was sine of pi over 2. It could have been something else that gave you 1. So I usually look in the denominator to get this value, or I look there. They should be the same. Okay? So what this question is really asking for is it's asking for you to find f prime of pi over 2. But last time I checked, we can't find, like I said, a derivative until we have a derivative function, and then we can plug in. So I'm going to find my derivative function, and then I'm going to plug in pi over 2 into it. So I'm going to go with f prime of x. In general form is going to be cosine x. That's what we established as a derivative of sine. So now I'm finding f prime of pi over 2. That's cosine of pi over 2, and cosine of pi over 2 is 0. So my answer for that one is 0. Okay, we've got one more left. Let's tackle this last one, and I think you'll be a master at using the limit definition of the derivative. So this one, I've got my good old h. I'm back to h. You might want to compare this to what you had in the first few examples that you did, but there is a difference here, and the difference is they don't have an x. So in the last ones, we had something like limit as h approaches 0 of f of x plus h minus f of x all over h. And the difference here is that my h is gone and I've got an a. It's f of a plus h minus f of a. So a couple problems. It's actually now harder to figure out my f of x function. And I've got to go one step further, just like I did in the last example, to find the derivative at a point. So the first thing I'm going to do is I'm going to try to draw out what is that function, because I need to eventually get to f prime at some point a. Okay, so that'll be my end goal. So my f of x function, if I look at my f of x function, perhaps it's easiest to, I don't really know, I think it's probably easiest to look at this piece here instead of looking at this, because again, instead of putting cosine of pi over 4, they could have actually put radical 2 over 2, and then you wouldn't have known. So it depends. Sometimes they make it a little trickier. So I'm going to look at this and try to figure out what my f of x plus h is, because it can't be evaluated. If you've got that pi over 4 plus h, it can't actually evaluate it. So I'm drawing from this that my f of x is cosine of x. Now just think about it. If you were actually asked to find f of x plus h, then you would write that as cosine of x plus h. And all I've done is put an x value in there. So I don't actually need that right now, but I'm just kind of figuring out, okay, is that actually my function? So I'm trying to find derivative, so f prime at, I'm actually looking for f prime at what? Well, what's my a value? My a value is this guy, which is that pi over 4. So I'm actually looking for f prime at pi over 4, but I need to first find f prime of x, and then I'll plug in my particular value. So back to f prime at x is a negative sine x. And usually these aren't complicated derivatives, guys. Usually the hard part is like working backwards. So now I'm looking for negative sine at pi over 4. And sine of pi over 4 is radical 2 over 2, so I'm getting for an answer for that negative radical 2 over 2. And that's my answer, because you were trying to find f prime at a particular value, and it was at pi over 4. Hopefully that helped. Let me know if you still have more questions on those types of questions.